weather looked pretty interesting, so I appreciate you coming over here. Um, this is basically the stuff. I want to start off with the stuff that you should probably take away from this. I think it's probably, if you're not already familiar with this stuff, it'll probably be a little bit too much to digest in 30 minutes, but these are the kind of the main takeaways. I wanted to mention Rudolf Kalman. He's the guy who obviously invented this algorithm back in the 1960s. Very famous and distinguished scientist and inventor who actually passed away about 2 months ago. It sounds like something that you would use on Star Trek, but it's actually an algorithm. It's a recursive algorithm. And it's very strongly connected to this idea of state space models of time series. One of the key ideas is that it combines sources of information to give you a better estimate than you could get with either of them independently. And a lot of different time series models. Still can't hear? Okay. Is that any better? Okay, I think I might have been blocking the microphone. And the other thing is just ubiquitous. It's used in all sorts of applications. Most of my examples will focus on econometrics applications, but used for spaceships. There's probably some implementation of it in the laptop that you're using right now. Some preliminary notes. One, I'm using a development version of statsmodels. I don't think the release version has any of the state space stuff in it yet. I just built from source, but I think this is version 8, the release candidate. Maybe I should just use this one. Does it help better if I hold it like this? So if you look at the development version of the stats model source, you'll actually see there's 2 versions of Kalman filters. One is an older version, which I think is in the actual current release version, which is used for parameter estimation on what are called autoregressive models. Also, I'm using the terminology for Kalman filters that's from a book by Durbin and Koopman called Time Series Analysis by State Space Methods. There's a lot of information on these out there, and it's used in a lot of different domains, and so you'll see different variables using equations, different terminologies, different ways of explaining how this thing works. This is kind of the econometric view of the world. So this is where we're going to start. The basic place I'm going to start is just a very simple time series, which is a random walk. It looks... I'll have to probably reduce it on next ones. So say that we have a second time series, which is just that first time series plus some noise. So the original time series is the blue dashes. The series with the noise is the green line. So basically, what you're asking with the Kalman filter, in a very simple sense, is if we don't have that original blue time series, what can we infer about it from just this noisy green time series? So this example is actually a very simple version of what's called a state space model. This is called the local level model, but basically all state space models have this idea of there being a state equation and an observation equation, or sometimes called a measurement equation. That first equation that described the random walk is our state equation, and the second equation, which describes that series plus the noise, is the observation equation. So it's called the observation equation because the y values are the things that we expect to be able to observe, but we're trying to get back to information about the alphas, the actual states. So these are just some quick examples of what that might mean. Obviously the sort of generic idea of having a signal plus noise, That's actually where this idea of it being called a filter comes from. Is, you can think of this in terms of signal processing. You have a noisy signal that you can measure, and what you really want to do is filter out the noise and get the original signal. The state may be the position and velocity of a vehicle, a spaceship or a robot, and what you can actually measure is measurement from a sensor that's a satellite or a GPS or something like that. Another example I've seen is you want to anticipate what a commodity price is going to be, but those don't change quickly enough because you only get information on those when people bid on that commodity. But people bid on futures more frequently, so if you have futures prices, you might be able to infer commodity price from futures prices. And my trackpad example, if there may be a Kalman filter in certain computing devices, just to keep track of where your cursor should be based on where you're moving your finger. That's still good. So this is what a linear state space model looks like in general. I'll cover this more later, but basically all we've added here are some equations, some terms that make this more generic. So in the state equation, we now have these terms T, which is sometimes called the transition matrix, which sort of describes the dynamics from one step to the next step. And this matrix Z in the observation equation is sometimes called the design equation. It sort of relates how the state values are connected to the observation values. So I'm going to jump into the way statsmodels does this. In particular, this is the development version that Chad Fulton developed. So this is hopelessly old school, much like myself. So this is basically a UML class diagram. On the right-hand side is basically the series of classes in statsmodels that define the time series machinery, at least as it's used in the state space stuff. And on the left-hand side is another class hierarchy which describes the state space model. And the way they're connected is through this model called MLE model, or maximum likelihood estimation model. And basically what that allows you to do is use the Kalman smoother as a way to determine the parameters given a time series. So if you have a time series as input and you need to estimate means and variances in that time set, this MLE model will let you do that using the machinery of stats models. So what I'm going to do now is, this is not something you should probably do in general, but what I'm going to do now is I'm going to create a Kalman filter class and specify that first initial simple model that we use just by manually plugging in the various matrices in the state space model. In this case, they're literally trivial because they're either matrices of ones or constant ones. But this is enough to define a state space model given the Kalman filter class. And the next, what I'm going to do is, once I've defined it, I'm going to simulate it. So again, you'll see a simulation here, which is fairly similar to the set of time series I showed in the first couple of slides. So this visualization is trying to explain some of the terminology of the Kalman filter and state space stuff. So when you get the new observation and you're trying to determine the best estimate for the next state, that process is called filtering. And what I was trying to denote that with the vertical line here. So if you are trying to predict points into the future, that's forecasting or prediction. There's also another process called smoothing. Smoothing goes backwards in time, but basically what you need to do to smooth the states is you need to run the Kalman filter forward up until you've gotten all of the points in the time series. And then you run a process backwards to basically interpolate new states or smooth them. Excuse me. The green triangles here are examples of what you would call the filtered state. So typically what will happen is that as you get new observations, you estimate a state, the filtered state, which you hope is closer to the actual state than the observation that you get. The vertical line between the last observed point on the red line and the state AT, sometimes called the forecast error. It's also called innovation. So that's basically the difference between what your next best prediction is if you don't know the next observation, and the best prediction if you do know it. So I won't expect you to digest this right away, but this is one recursion for this particular simple model. Basically, each line corresponds to one step in the process. So the first step, we determine what's called the innovation, the forecast error from the new observation, we calculate its variance, and then we calculate the filtered state and forecast states. So what we're really trying to determine is a new conditional distribution, so a distribution of the state given the observations that we have. What we start off with is some estimate of the state at prior to that observation. And what we sort of know is we sort of know the distribution of the possible next states, and we sort of know the distribution of the possible errors in that next state. And so what these histograms are trying to show is if I know the state, if I know the current state, I can sort of predict the next state just based on the distribution I know at that time, which is the sort of blue histogram. The green histogram is the distribution of possible forecast errors for the next state. So what we know when we get the next observation, which we're calling YT, now we can actually calculate the actual value for that forecast error, VT. And we also, in a sense, know the relationship between the next state and that forecast error. And if this slide seems out of place, and it made your head spin a little bit, I apologize for that, but just roll with me here for a second. So there's many ways to explain this idea. This is the one that Durbin and Koopman use, and I like. It seems to make sense to me. This is a simple lemma, mathematical lemma that has to do with basically linear regression. So this applies to least squares regression. So you've got these two variables, A and B, which are jointly distributed by variate normal distribution. And this lemma says that the distribution of A given B and the variance of A given B correspond to these two equations on the bottom. So this is important for a couple of reasons. So we can use our state, our next state alpha t, and the innovation VT as A and B. I'm going to focus on the covariance between the two things. So if you work through this, it turns out the covariance is this value PT, which is actually the covariance of the state at the current time period. And you'll see that this particular ratio, PT over PT plus sigma epsilon squared, comes up twice in these equations. And that ratio is called the Kalman gain. And I put a box around it because it's kind of the key idea in the Kalman filter. And so intuitively what this means is that if the noise in the observation is small, then this ratio is going to be close to 1. And so that means that the value that you observe is probably pretty close to the actual state. And so you want to move your estimate to that closer to that actual observation. If the noise in the measurement is large, on the other hand, then this ratio will get progressively smaller, and that means that you're probably better off staying closer to the state that you estimated without the observation. It's also worth noting that using that lemma on the previous page and what's shown here, this is actually the optimal estimate given a linear system and Gaussian distributions, much like least squares regression. So on that slide earlier, we talked about filtering, and basically filtering is, again, the idea of trying to find a better estimate for the current state given the latest observation. What you're really trying to find is this conditional distribution. So if we just use our Kalman filter model that we used before, what I'm going to do is I'm going to cheat and initialize the initial known state to something that I already know. And then I'm going to bind that y, the observations, to the Kalman filter. And then I'm going to run the filter forward. And what you end up with is something like this. Is that large enough for people to see? So y is the set of observations, and the red dashed lines are the actual states, which, you know, in normal cases we don't know, and the blue dots are the filtered state. So with forecasting, it's a very similar process, except what we're looking for is the next value in the time series, and the trick of it here is that we don't have an observation for this. We're just trying to estimate the next point in the time series, given what we know about previous observations and the state. Again, we're really calculating a conditional distribution. So this is a forecast out for, I think, 10 time periods given our so-called local level model, and you'll notice that it's basically a flat line that runs from the last estimated state, and that's pretty typical of this particular model. So once you no longer have observations, the forecasts being carried forward are basically the mean of the very last state that you were able to determine through filtering. And again, this is like the simplest case of forecasting. Just to back up a little bit, there's a lot of things we ignored in this discussion so far. So one of them is that I've assumed that I already knew these parameters, these variances of the time series that I'm starting with, which is generally not the case. Normally you need to take the data that you have and estimate these parameters from the data. That's essentially what the Kalman smoother does. But that's why when you're using the models in the statsmodels state space package, typically you want something that's derived from this MLE model class, because that class will do this process for you using the normal statsmodel time series machinery. We also typically don't really know what the first state is, and so there needs to be some way to initialize that first state. A fairly common method, and one that seems to work pretty well in a lot of cases, is what's called the diffuse prior, which is kind of a fancy term for guessing. So basically you say the mean is 0 and the variance is ridiculously large, and we'll start from there. So when you move on to more complicated state space models, the recursion for the Kalman filter gets a little more complicated. And again, I realize this is not super easy to read, but the same idea holds here. You've got one set of equations at the top you've got 3 lines of equations, one of which is calculating the next mean value, and on the right-hand side, one of which is calculating the variance of the distribution. Mainly what's happening here is you're introducing the T matrix, the transition matrix, to make the dynamics a little more interesting, and the Z matrix to make the relationship between the state and the observation more interesting. So the next example I'm going to show is what in stats models called an unobserved components model. If you've worked with time series models, you might also call this a structural time series model. So it's a type of model where the time series is divided up into a bunch of components, you know, a trend and some random mean, and a trend and possibly a seasonal aspect and so forth. I'm going to do a really simple structural model which just has a random trend. So this is the data that I'm starting with here is industrial production data from Fred, Federal Reserve. And this is what this model, this local, this is called a local level model, or local linear trend model. This is what it looks like in state space form. So those three equations at the top describe the model, and then the ones at the bottom describe its form in state space form. And this is basically how you set it up in stats model. Basically, I'm saying I have a level and I have a trend, and both of them are stochastic or random. And then I fit that data set to get the parameters that I need. I'm not showing the summary of the model because it fills up way too much space on the slide. I'm not sure if you can actually see it here, but when you do forecasts with this local linear trend model, what you basically end up with is a line with more or less constant slope. It's kind of hard to see the slope here, but there is in fact a slope. And it will, again, the Kalman filter at this stage, since our T matrix and Z matrix don't vary with time, will have reached a steady state. And so every forecast after we have observations is just going to give us this constant trend. The gray part is the uncertainty, the confidence interval in the forecast. And so I think the basic idea it's trying to convey is that the further you get away from having an actual observation, the more uncertainty you have. I think that's fairly intuitive to understand, but it's fairly well spelled out in the math of the Kalman filter. Another reason why state space models are popular with economists in particular is that a lot of time series models can be put into state space form, including the whole zoo of what are called ARIMA models. This is just a simple example of what's called an autoregressive model. And this is the top equation is the normal autoregressive time series model, and the stuff at the bottom is the state space form of it. And these are the design, transition, and the R matrix is what's called the selection matrix. And basically that maps, so the shocks that we have, the random parts in the series now come from a multivariate distribution. And this selection matrix basically says, I want to take, since it's only 1, 0 here, it says I just need one random component. So it's basically, if you look at the previous slide, we just have an epsilon there. So the R matrix is basically selecting one element from this bivariate distribution to add it as an error term. So I'm trying to build a model here using what's called a Ceramax model, which again is one of the implementations in the stats model state space library. And what I'm trying to accomplish here is to forecast electricity demand in the industrial sector. Having read some papers on this, the common idea is that demand is affected by industrial production and the price of competing energy sources. So this is what industrial electricity demand looks like. And probably the first thing you notice is that there's a fairly prominent seasonal aspect to it. So the first thing you want to do in this type of model is figure out what that seasonality is. And this is monthly data. So typically that means 12-month season. This is the stats model seasonal decompose function, which does a lot of the work for you to show you the seasonal parts and the trend in your data. So the top series there is the original data, and the line in the second row down is the trend in the data. The third row down is the seasonal component, and the part at the bottom is the residuals. The residuals ideally would look like white noise. Here they look like they probably have a little bit of structure to them still. So I don't want to go into this too deeply, but if you're doing these types of ARIMA models, basically the thing you have to do is you have to figure out where the autocorrelations are in your data. And typically the way you do that is you difference the time series to find the seasonal aspect, you difference the time series to find any other autocorrelations. And then you can plot these autocorrelation and partial autocorrelation diagrams. I don't know if the top, these are actually features in Stats Model 2. These plot ACF and plot PACF functions will plot these autocorrelations for you. And so roughly what this shows me is that there are significant components at both the 12-month lag in the partial autocorrelation and the correlation, and possibly a significant lag at 1 month. It turns out it works off better if I include the autocorrelation in that, but not the moving average part. Excuse me. And again, I think it got cut off, but this is in Stats Model how you set up this type of Seramax model. This particular example, all I'm using is the original time series. There's no so-called exogenous data, so there's no regression variables in here. So this is what a forecast looks like of this time series using the state space model and the Kalman filter. You can see that it does pick up the seasonal part and the autoregressive part in the time series, and the gray part is the confidence interval of that forecast. This next model is basically the same thing, except in this case I am including the extra so-called exogenous variables, the industrial production variables, the energy price variables. And again, the difference on this particular one is that to do this forecast into the future, you also need future values of the exogenous variables. And in fact, that's probably why you would do a model like this, because those variables may be easier to access than the variable that you're trying to forecast. But in this case, what I've done is cheat and leave out the last 2 years and treat those as data that I'm predicting. So what this shows is that, again, the green line is the forecast, and the gray area is the uncertainty in the forecast, and the black dots are what the original series has. So do I have enough time? Yeah. I just want to go over a couple of extensions to the Kalman filter real quick. One common thing is there's something called the extended Kalman filter. So one thing that I probably didn't make clear in the earlier slides is that this is essentially a linear dynamic. So you're multiplying the previous time step by a matrix, and so it's a linear relationship. A lot of times that doesn't work, and so people have created what's called the extended Kalman filter, which allows you to have nonlinear dynamics in the Kalman filter. There's a variation called the unscented Kalman filter. And then recently there's been a lot of interest in what are called particle filters, which they're much more computationally intensive and more difficult to explain, but they take a lot of the assumptions out of the process. There's no assumption about the distribution of the data. There's no assumption about stuff being linear. And that's about it. You know, I recommend Durbin and Koopman's book if you want to learn about this. Koopman also wrote another book on state space analysis, which is a little bit simpler. And there's this blog post called How Kalman Filters Work on the Uncommon Lab website, which if you can only read one thing about these, I highly recommend it. It's very, very complicated and lengthy post, but it covers everything from particle filters to the basic Kalman filter. And if you can work through it, it's a really, really good piece of work. That's it for me. No idea. Okay. Covariance estimation for
the ensemble.
the ensemble Kalman filter.
Not to my knowledge.
Yeah, I think there's an assumption that if you have, I think part of the reason is that this is not a particularly good model. It turns out that some of these energy variables, which are supposed to be good predictors of electricity demand, don't seem to be. For instance, coal price does not really seem to be that good of an indicator of industrial electricity. But I left it in just to see what would happen. So I think probably just the issue of not having a very good model is more to blame here than not having more observations. Oh yeah, definitely. Sort of. I mean, I'm not entirely sure that that's true. I mean, the Kalman filter should, to some extent, update as you go. I mean, one issue that I did not have time to explore here, just for time constraints, is the dynamics in the state equation can be time dependent. So in most of these models, it'll reach a steady state at some point, and then everything after that, it doesn't really update the Kalman filter anymore. But you can have situations where you can make those vary by time, and so continuously, it will update them as you go. I personally have not had situations like that, but it is actually one of the key features of the Kalman filter is that it deals really well with missing observations. In fact, forecasting in the Kalman filter is effectively the exact same thing as predicting the state without an observation. And so, for instance, in the one of the variables that you can use for this electricity model is gasoline prices. And for reasons I don't understand, when you download that from the federal government, sometimes they just leave out months. But it's relatively easy. It's much easier with the Kalman filter and state space models to do that, to handle that kind of data than it is with normal estimation methods, normal time series methods.
So I know Chad is actively working in that direction right now. There's a good issue about this. The way it was written originally is you have to have this fixed frequency data. But as you've heard, the Kalman filter handles this, and then so Chad is adjusting the dynamic of the system.
Probably R. That's the most probably developed area for common filters. I believe that that Uncommon Lab blog post, I believe they do most of their work in MATLAB as well. And I don't know I don't know of any particle filter implementations in Python yet. So, but they are in R and MATLAB. I'm sorry. Yeah, I put them on my about an hour ago. Um, so catch is that this is an actual IPython notebook. So when you look at it on GitHub or if you download it, it won't look like the slides unless you install Rise. But yeah, there's a link on my Twitter handle is Quickstep, KWIK step, and there's a link to it there. Um, it's not a Kalman filter per se. Um, you can even and it's also the base implementation is in Python and C. So if you have a lot of data, it's still pretty fast. Um, well, I guess I think of them as being in slightly different realms, but I mean, you could conceivably use k-fold cross-validation to do out-of-sample validation of a Kalman filter, I think. It's kind of hard to do cross-validation on time series. It's sort of a black art, but yeah, I guess the place where you would choose to use Kalman filters as opposed to more traditional time series techniques, I think, are one, you have non-stationary data. So if you don't know what non-stationary means, then you probably don't care. And the other one is you have missing observations. I think those are really those are two cases where the Kalman filter really is superior to normal time series models.